Recording is rolling. It is Wednesday, September 18th. Here's Top Scientist for projectile motion. I do have different kind of classes. I'm going to do this one video for all my classes today. So here's all my honors classes. Awesome job. Teaching this class so many years. Here's a conceptual class. A lot of students think projectile motion is some of the most difficult stuff that we do. So yeah, so definitely awesome job if you are on any of these Top Scientist lists. Here's my AP list right here. So AP, conceptual, honors. So awesome job, guys. Projectile quiz, projectiles. All right, so of course we're moving on to forces, Newton's laws of motion. Yesterday, you guys did a spring scale lab, right? Spring scale lab, and most of today we're gonna go over the ideal solutions to every one of these mini labs, because these are concepts that are gonna show up over and over and over for the rest of the class. So this is a pretty big lab here. There's a lot of good information in this one. Right. Oh, some of what you're going to see today, here, I'm going to throw this term on the board. Free body diagram. A lot of times I'll abbreviate this FBD. This is just a diagram where you're labeling all the forces. You guys have seen different types of vectors so far in this class. You've seen displacement vectors, velocity vectors, acceleration vectors. Now, when I draw one of these diagrams, I'm just going to draw the force vectors. And then in the future, I might talk about like moments or torques, has like a rotation type component, but we're not quite there yet. So for now, I'm just going to do forces. All right, puzzle assignments. So I'm getting puzzles together for each of my classes. For my honors classes, this is chapter 5, or chapter 4 and 5. So chapter 4 and chapter 5 in your textbook. For my AP class, it's chapter 4 in their textbook. So these are all related to these forces. And my conceptual students, I'm working on getting that together. But it is something a little bit different with them. Right. So there is not a due date yet on any of these assignments, because I have to show you guys how to solve these first. But for that, I have to debrief the spring scales lab, which has a lot of the same concepts in it. Okay? Right, but I want to get that in your hands so you can read the questions and get an idea where we're going with that. All right, so you guys good with everything so far? All right, ready to head into this lab. So again, I want to go over with you guys what are the ideal answers to every one of these and a bunch of tidbits along the way. Here we go. Very first one, number one. Just very simply hang different masses and say, what is the weight? Make a graph. So I'm going to make up some. You guys had a whole box of lab weights. Your largest lab weight was 1 kilogram. I'm going to record this in grams. Guys, how many grams is 1 kilogram? 1,000. So I'll go ahead and call it 1,000 grams. Now, in the math in this class, a lot of times you go ahead and stick to kilograms, but today maybe I'll just throw grams in there, right? Oh, the second biggest one, that was like 500 grams. Right, the numbers, of course, are stamped in the lab weights. So this says 500 grams on it. Oh, there's a 200 gram guy right here. 200 grams. Ooh, this guy was like 100 grams. Let's do that. 100. It could be grams. Right. And then you pick each of these up with a spring scale. So let's say, how about the big one? How about the 1 kilogram? If you pick this up with a spring scale, it reads how many newtons of weight? 10. That was 10, wasn't it? So go over here. You got to write 10, and then the unit is newtons. Right? You guys got that? Right. You know what? Oh, turns out the number is not exactly 10. Does anybody know more precisely what that number actually is? Take a guess. I bet you can guess. 9.8. It turns out it is 9.8 newtons. Now, I'm just going to round it to 10 newtons, but just so you know. Right. Well, that's 10 newtons. What do you think the half the mass weighs? 5 newtons. Hey, what about the 200 grams? How much does that weigh? 2 newtons. How about here's 100 grams right here. If I lift it, how much force does that take? 1 newton. Yeah, that's a good rule of thumb, right? At this kind of medium, small size lab weight is 1 newton to lift it. Right? Now, remind you guys too the difference between the concepts of mass and weight. Right? So if I lift this versus if I push it horizontally. Right? Suppose I take this to the moon. Right? So now we're comparing Earth and the moon. Say we've got like a video feed. We're talking to each other, right? So I'm down here on Earth, right? Somebody's up on the moon, and we're both doing this with a 1 kilogram lab mass, right? Guys, 1 kilogram. Is it equally difficult to do this on the moon as on Earth? Does it feel exactly the same? Yes, it does. Yes, it does. This feels exactly the same on the moon as it does on the Earth, right? That's 1 kilogram of mass. That's something to do with inertia. But what if I pick it up? Now is it easier to pick up on the moon? Yes, it is, because the moon, a lot less gravitational field, less gravitational force, less weight on the moon. So on the moon, 1 kilogram is still 1 kilogram, but it's going to weigh a lot fewer newtons. Let's do a graph. Most students were pretty good with graph, but some of you guys are still trying to figure out graphs. So I'm going to put force in newtons on this axis. Let's do mass and let's call it grams on this axis. So here's a good way to make graphs. Find the largest value and plot that and scale everything else accordingly. So 1,000 grams. So I'll put 1,000 and then grams is already embedded right there. There. And then I can scale this. So halfway would be 500. Of course, it's going to start at 0. And then 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. You guys see how it's scaled evenly spaced, 100 grams at a time. Let's do this for force in newtons. Okay, it goes up to 10 newtons. So I can put 10 right there, starts at 0, halfway is like 5, and then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. You guys see how they're all evenly spaced? You guys see that? Okay. So let's plot these like Cartesian coordinate points. Right? You do that? So see, for 1,000 grams, that was 10 newtons. So 1,000 grams out here, that's like, see, is that about right? 10 newtons, bam, bam, yeah, bam, right there. Right. So that's that coordinate. Right? For 500 grams, that was 5 newtons. 500 grams at 5 newtons, it's right about, bam, right there. 200 grams has a weight on Earth of 2 newtons, bam. And then 100 grams weighs 1 newton on Earth, bam. Right, so those points right there. You guys see that? Put it all together. Is that, you guys see a nice direct relationship between mass and weight? Direct relationship? Right? Let's come up with an equation for that. Equation time. So this force is actually the weight, right? So I'm going to write weight equals, so it's like saying y equals, right? Force equals weight equals. Right? Well, it's kind of like y equals mx. There's some slope of this graph. There's some slope right here. And then you can have variable masses and they're going to have corresponding weights. There's a direct relationship. What does the slope of this line represent? Or maybe you can think of a numerical value for it. Or what could it physically represent? What is the slope equal to? Got masses, it got weights. What's that relationship? Hey, how about this? Huh? Oh, okay, yeah, it is a type of acceleration, true, right? Although it's rest, it's not actually accelerating, but although it is something to do with the acceleration. That's interesting. Right? What if I did this on the moon, where I could have the same masses, but they would weigh a lot less? Could that be a line that looks like this? It would still be linear. What if I do it on Jupiter? Do you think everything would be really heavy? Yeah, it would still be a straight line, but it'd be like this, really steep. So I can call this the gravity field, G, which if you did release it and let it fall down, that would now turn into an actual acceleration. Would be accelerating that much. So let's go finish this equation then. So we're gonna do this mass times this gravity field. Well, slope times independent variable. It could be like G times M. But I'm gonna swap that around and call it mg. Is that, you guys see that expression right there? Weight equals mass times gravity field. Because from now on in class, whenever you see mg, I'm referring to the weight of an object. It's multiplying 2 variables together, mass and gravity field. So if I make a free body diagram, ooh, guys, is that a new term? Free body diagram. On this weight, it's got 2 forces on it. The force pulling down is m times g. That's the weight, which could be like 10 newtons in this case. Well, for the big one. Right? And there's a spring scale force pulling up. Guess you notice I put a dot right at the center of mass of the object, as if it's a single point. And I'm drawing vectors coming from. These are force vectors, and I label them. So mg is the weight, and then I have F sub s could be the spring force. That's a subscript s holding it up. Right? Is that right? We got a little free body diagram right there. We call that FBD, free body diagram. Okay? Real simple one. Force down, force up. Right? Is that okay? All right. Next one. Next mini lab. What if you have one weight that you keep using over and over? Let's say the big guy right here. All right. And you use 2 spring scales, and maybe you distribute the weight a little bit differently. You kind of toggle them back and forth. Lift this one a little bit, a little more slack in that one. So let's call this a 1 kilogram lab mass. give you guys kind of a textbook answer for this, which weighs how much? Is that 10 newtons right there? 10 newtons? Okay, so 1 kilogram weighs 10 newtons on Earth, I'll be sure. 9.8 newtons, I'll call it 10 newtons. Okay. Now, if you distribute the weights evenly with these two spring scales, they would read how much each? Is it 5 and 5? Yeah, okay, it's gonna be okay, yeah. So it could be, oh, and I gave you guys a table here. What's the left force? What's the right force? So it could split 5 newtons and 5 newtons. Okay, so it could be for a total of 10 newtons up. Oh, and that could balance the 10 newtons down. So you got 10 newtons up, 10 newtons down for a net force of 0 newtons. Hence it could be at rest, equilibrium. Okay? But what if you shift them around a little bit? What if this left one is only holding up 3 newtons? What is the one on the right holding up? 7 newtons. So it could be 3 newtons on the left, 7 newtons on the right. Again, for a total of 10. So 10 up balances with the 10 down so that overall it zeroes out. Right, guys, okay? Right. How about this? What if the left one is only holding 1 newton? What's the one on the right holding? 9 newtons. You guys see the rule. Right? Adds up to 10. What if the left one is holding 8 newtons? What's the one on the right? 2 newtons. Again, for a total of 10 newtons up, balance 10 newtons down. Let's make a graph. What's the left force versus the right force? I'll put in newtons and then the unit also newtons. So, okay, it maxes out at 10. Let's throw 10 on the board right here. 10, 10. Okay, well, half of that could be 5. It starts at 0, 5. Okay, then. Okay, so now I got everything scaled. Good. All right, so make a graph. I'm going to treat these like Cartesian coordinates. So I put this a little bit backwards, but here's right, here's left, right, left. So over 5 up 5. So over 5 up 5. Bam! Is that point on the board. Over 7 up 3. Over 7 up 3. Bam! It's right there. See if one's taking more force burden, the other has less force burden. Over 9 up 1. 9 up 1. Bam! Is that point on the board. Over 2 up 8. Over 2 up 8. Bam! Right there. Okay. Hey, could I put all the force on one or the other? Would that be like 10, 0? Bam! Or 0, 10? Bam! This could be points too, right? Right? If you put all slack in one and all force burden on the other. All right. Now the graph definitely pops out of the page there. Isn't that the relationship I'm looking for? So it's both linear and inverse. Right? So it's linear but not direct. It is an inverse type relationship. You guys that too? Right. So will you ever see that graph again? Maybe, maybe not. I don't know. Right? But one of the things I want you to get out of this class is that not to just necessarily memorize a bunch of stuff, right? But to understand how things work. So if you understand the principles of what are the laws of nature, then you can get any crazy question out of left field and kind of figure out how that kind of goes together. Okay? You guys can do that? Okay. You guys ready for the next one? All right, this next one's a pretty big one. We're about to go into 2 dimensions here. 2 dimensions. Ooh, this one's gonna be fun. Take some time. So let's bring back our big guy, 1 kilogram. So I'll throw 1 kilogram right there on the board. So this thing I know weighs 10 newtons. So down force of mg equals 10 newtons. We can do it like that, right? Right. And I bet this bottom spring scale has to be pulling up with a spring scale force of like 10 newtons, right? And if everything's straight vertical and you hold everything symmetrically, how much spring force in each of these top spring scales? What and what? Is it 10 and 10 or 5 and 5? Yeah, I have to split 5 and 5, right? So, okay, so I got a table of values here. So what's the force on the bottom spring? I'm just gonna use the 1 kilogram mass, which weighs 10 newtons. So I got 10 newtons on the bottom spring scale, okay? And then this next column says each top spring scale. I guess if I was a bit more scientific about it, I really should have split this in 2 separate columns. All right, so it's okay if you do that. But if it's symmetrical, then ideally they should be the same number anyway, okay? If it's horizontally symmetrical. So in this case, it'd be 5 and 5. So I'll go ahead and record each one, but if you just put 5 newtons, they could each be 5 newtons. Okay. Now, that's if they're all aligned 0 degrees from the vertical. You guys see, I set up a diagram on the very last one with a dashed vertical line. and I'm labeling this angle theta with respect to that. So as you guys are spreading out like a Y shape and then a wider and wider Y and closer to a T shape, you can record the angles with respect to the vertical. I didn't have to do that. I could do it a different way, but just how I set it up, right? So the protractor, you guys found the middle node right in the middle. Take the node of the protractor, park it right there. You zero out the vertical, align that. And then this spring scale will sweep through an angle. And if as long as it's symmetrical, then the one on the other side sweeps to the same angle on the other side. Right? And you say, how many degrees is that? You guys see that? Right? Now, guys, if you approach a perfect T, if you had a perfect T shape, how many degrees would this angle be right here? How many? 90. So, okay, so kind of go up to 90, maybe, or at least it could approach 90. Right? I'm going to make up some angles. Let's go 30 degrees, 60 degrees. We're going to throw in 80 degrees, right? Now, as you spread it out, get a wider Y shape, you get closer to a T. What happens to the force reading on the bottom scale? Does that stay the same? Yeah. So if it was 10 newtons to start with, and I'm using the same lab weight, I bet it's 10 newtons there, 10 newtons there, 10 newtons there. I'll go ahead and fill that in. 10, it should be the same number all the way down. So for me, it might be like 10 newtons all the way down. Is that okay? But what about the top spring scales? As you spread it out, did it take more and more force to pull those? And was that show, especially the closer to a T shape you got it, were the readings going up? Were they increasing? Right here, I'm gonna fill out this last column, this like split column. I'm gonna make up an equation here. Make up an equation. Right? I'm not gonna say where this is coming from yet, but in a few minutes, I'll show you guys where this is coming from. I'm gonna start with that 5 newtons right there. I'm gonna divide by cosine of whatever angle from the vertical. So let's start with 0. Right? You guys know what is cosine of 0? It's 1. 5 divided by 1 is 5. Okay. Oh, look, and that's also 5 newtons. So 5 and 5. So that could work for a straight vertical. It's okay. Right. All right. So I'm going to make the case that this is going to work all the way down for all these angles. Right? And I'll show you guys later where this equation comes from. So kind of hold you guys in suspense a little bit. Let's pop in, 30 degrees. Right now, 30 degrees, that's not great. I bet the force went up a tiny bit. Let's see how much. Ooh, 5.77. Can I round that to about 6 newtons? About? Okay. So it did go up, but it was really subtle, right? Went up a little bit, right? Let's try 60 degrees. What if I pop in 60 degrees and whoa, before I hit enter, I want you guys to see what the answer is going to be before I hit enter on that calculator screen. Guys, how about this? Guys, if this angle is 60 degrees from the vertical, then what's the total angle between the two spring scales? 120. And if that's 120 degrees, and this thing is horizontally symmetrical, then what is this angle here and this angle here? 120, 120? 120, 120, 120. Okay, so wouldn't that also be radially symmetrical? Right? Let's change the story a little bit. What if this is a 3-way tug of war? I got 3 ropes all tied together, and we're up in a helicopter looking straight down, aerial point of view, looking straight down from a helicopter. You guys see 3 guys playing tug of war? Tug of war. Okay, 120 degrees between each set of ropes. If that's true, then would each rope have to have exactly the same tension in it? Would that be true? I think it would. Okay, now let's go back to the story from yesterday where we got the lab weights and the spring scales. Okay, now we turned it vertical, but I bet mathematically it's identical. So if this is a 60-degree angle, so we got 120, 120, 120, radial symmetry, and the bottom spring scale is reading 10 newtons, then what does each top spring scale also have to read? Is that 10 and 10? 10, 10, and 10? Let's see if I'm right. Let's see. Okay, so 5 newtons divided by cosine of 60 degrees is, look at that. 10.00000. It's 10 exactly on the nose. Yeah, it is. 10 newtons there, 10 newtons there. Is that? All right. I still haven't explained where this equation comes from, but hang tight. You guys will see it in a few minutes. Okay. Let's jump up the angle to like 80 degrees. I'm getting closer to 90 now. So 80 degrees. Whoa! It jumped way up to like 29 newtons. And that would be for both sides. It's symmetrical. You guys still got that? 29 newtons. You guys got? All right. Let's graph this. That goes up to almost 30 newtons. So force on each top spring scale in newtons. I got 10, 20, 30, 10, 20, 30. Okay, so it starts at 0, of course. Okay. Let's plot these points. So at 0 degrees, it was 5 newtons each. Bam, that's that point right there. At 30 degrees, it jumped up to a little bit to 6 newtons, but it's really subtle. So bam, that's about 6 newtons there. At 60 degrees, it was 10 newtons. Ooh, now we're on the move. Let's go 10 newtons at 60 degrees. Bam, that's right there. Right now, so far, if you look at those points, you see it's starting to slope up a little bit. Right, it's really subtle. At least so far it is. Now let's try 80 degrees. It's 29 newtons. Woo! 29, it's way up here. 29, 80 degrees. Bam, that's about right there. So there's my 4 points on the board. Wow, it's starting to really take off, isn't it? You see that? Huh. Hey, what if I did 90 degrees? Let me try my calculator trick. Let's go 90 degrees. Because what is cosine of 90 degrees? Would just that part be 0? What is 5 divided by 0? Just blow up the calculator. Divide by 0. Error. How does that translate to a graph? What does that mean is happening at 90 degrees on the graph? That's called a source of the V. Vertical asymptote. That's what I'm looking for. A vertical asymptote. I'm going to dash off a vertical asymptote. My last class, they never heard that phrase, or I don't know. I'm going to spell this out. Vertical asymptote. Trying to look at word. Vertical asymptote. Right. And if you fill in the rest of the graph, did you guys fill in the rest of the graph? Do you think it's going to go kind of like this about? Pretty close. It's going to shoot off that way. You guys think? Right? You guys see it? Got a couple of questions down here. As this angle approaches 90 degrees, so top angle from the vertical, the force on each top spring approaches, guys, what number goes in this box? Infinity. Yeah, it just shoots up. Okay, that's what it means to approach a vertical asymptote. It just shoot off to infinity. Therefore, can you ever make a perfect T shape? No. You guys think, what if you're like, what if you're Arnold Schwarzenegger? You just like pulling as hard as you can. You have like super thick. Can you make a perfect T shape? No, you can never do that, because there always has to be some vertical component of the force. Okay, right, you guys got that? Right, I got a little bit more to say. I still have to explain where that equation came from, but to do that, I'm gonna have to show you guys some posters. You guys ready for some posters? Now, this one you guys have seen. Hooke's law. This is the principle by which those spring scales operate. If I apply twice the force, it's going to stretch the spring twice as much. So it's linear. Boom. Okay, so you guys agree with Hooke's law. Right. Moving on. Let's do. Oh, hey, this is the first mini lab you guys did yesterday. It's like this one right here. Okay. Oh, look, I have a free body diagram. It's exactly the free body diagram I just drew a few minutes ago. Maybe you guys were adding to your lab too. You guys remember that one right there? Right. Here's a nicer looking version of it. Right. So here's your lab weight. There's 2 forces. I got the weight down, mass times gravity field. That's weight. Right. And then there's a spring force pulling up. And you guys see that as long as it's equilibrium, for equilibrium, isn't it true that the sum of the forces has to go to 0? Right? So do you guys know what that is? The sigma, the jagged that you're looking at E, sigma, it means the sum of, right? So if I add up all the forces in the y direction for that matter, right, it has to 0 out. That's what that says, right? And if one's going up and one's going down, then you're effectively subtracting them from each other, right? Because one's up, one's down, right? So it has a 0 out. Oh, and spring force, what do you guys know that is from? Hey, whose law is that? Whose law? Hooke's law. That's F equals kx right there. And here's weight is mg. Hey, do you think if you know any 3 of these 4 variables, you could in principle solve for the 4th? Right? I might do this with you guys one day, maybe if we have time. What if you know the lab mass, you know the gravity field of Earth, and you know how much the spring scale stretches, x? Could you solve for the spring constant k? What is the spring constant of the spring right here? You could do that, right? How much is okay? Right, okay, that's in 1 dimension. You guys ready for 2 dimensions? Because this is all leading up to this so far. Ooh, all right, yep, okay. This one looks a lot closer to what we're doing, right? So I have a truss joint and tension. Now I do have some horizontal symmetry going on. So you could put a mirror right in the middle. Bam, there's a mirror, and the right side looks like the left side. Is that okay? Right. So now I have 3 forces. I got the weight pulling down, and each spring scale pulling diagonally. up to the left, up to the right. So you guys see three forces there, right? Right. Now, how can we make sense of this? What I'm gonna do, I'm gonna make the case here that you can introduce a Cartesian system that's like parallel to the ground, and then, well, perpendicular to the ground can be parallel to gravity. So maybe like parallel perpendicular to gravity, something like that, right? And rewrite these forces in terms of components. Well, the weight's already aligned to the gravity field, so that one you can leave alone, right? But what about the diagonal forces? Like how much over are they pulling? How much up? Oh, how much over? How much up? Does that sound like a job for sine and cosine? You guys think we're about to break out a sine and a cosine? Right? Okay, now here's your guiding principle. So one pulling up to the right and the one pulling up to the left, right? This guy's pulling to the right as much as this guy's pulling to the left. That's what this blue says right here. The sum of the forces in the x direction goes to 0. These two components zero out. Notice I dashed the components. I did not make them solid because I'm re-representing the original forces. If I drew them solid, I would be double counting. Okay. How about the in the vertical? You guys see all this green stuff? Green. Do you guys think that these spring scales pulling up, this up and this up, have to balance with the weight pulling down? And that's what this green bit says right here. It says the sum of the forces in the y direction, in the vertical direction, has to also zero out. This up and this up have to balance with this pulling down. Is that okay too? Is that? All right. Okay. Now, because this is horizontally symmetrical, right, the same diagonal just mirror flipped, right? If this lab weight, let's bring in this guy, bam, right there, weighs 10 newtons. You guys got that? 10 newtons? Right? How much strictly up is each of these spring scales pulling? What and what? 5 and 5. 5 here, 5 here, to balance out with this 10 down here. That's the screen step right here. You guys see that? Is that okay? All right. So next thing, I'm gonna. Oh, that's a bit here. Well, draw from scratch. That's up. Okay. Oh, here. I'm gonna draw some notes here. I'm gonna focus on. Do you guys see a nice right triangle right here? Nice right triangle. Okay. I'm gonna just focus on this bit of this larger story. Okay. So here we go. Okay. So I got a spring scale pulling up and to the right. I'll call it F sub S. Now, as you were changing the angle from the vertical, so this is subscript S right there. Right? You were changing the angle from the vertical. Here's this angle that you were measuring with the protractor. You guys remember? Zero that out. Bam. So many degrees. Right? That spring scale force was changing. Right? And if I'm looking at this poster, I'm saying, well, I'm going to analyze this in terms of how much over, how much up. So let's throw in some components. Notice I'm dashing the components. How much over? How much up? You guys see, I just, and those are vector components. They got little arrowheads on them. Is that too? Right, is that okay so far? Right. Ooh, you guys see this angle that you've been measuring all along from the vertical? Is that the same as this angle right here? Is that the same? Like if this is 28 degrees, is this also 28 degrees? If this is 41.5 degrees, is this 41.5 degrees? They're the same angle. Okay, is that all right? Same angle? Okay, so you've been measuring angles with the protractor. You're measuring the spring scale force by directly picking off the spring scale. But what I've been saying is that if you have a 10 Newton lab weight, you got also spring scale on the other side. Don't forget the one I didn't draw here, right? That this leg of this right triangle is always going to represent 5 newtons, right? Is that what I've just been saying? Right? Because remember where I got that from. If I have a 10 Newton lab weight, this has to pull up 5 and this is up 5. So this is like locked in place 5, regardless of what the angle is. And regardless of what the spring scale is reading, this is always pulling up with 5 newtons. Is that okay so far? All right. Okay. Now let's set up a trigonometry relationship. So here's what I have. At the hypotenuse of a right triangle, which is the spring scale, of course, I have some reference angle, because it matches this one. And I have one of the legs of the right triangle that's locked in place as 5 newtons. That's adjacent to the reference angle. You see adjacent? Anyways, if you go from hypotenuse to adjacent to a reference angle, what kind of relationship is that? Is that sine, cosine, or tangent? That's cosine, isn't it? Let's set up a cosine. You can say cosine of the angle is adjacent over hypotenuse. That's always going to be 5 newtons divided by whatever the changing spring scale force is, right? Or what I was really recommending to you guys a few weeks ago is to do a little algebra shuffle and actually memorize it this way. If I cross multiply the spring force going to be spring force times cosine of that reference angle. Always gives you, well, this adjacent leg, which turns out is locked in place at 5 newtons. Okay, is that true too? Is that? Okay. Let's go one more step. Suppose I'm solving for a spring force as a function of the angle. Now, why would I want that? Because that is going to get us closer to this graph. You guys see its top spring scale force as a function of the angle, right? So I'm really close to getting that. Can I just take this cosine of the angle and divide it down? Divide it down. So it's going to look like this. The spring scale force is equal to locked in place 5 newtons divided by cosine of whatever the changing angle is. I have lots of different angles. These be all different angles here, right? But this relationship should always hold true, right? You guys see where I get that from? A little trigonometry, a little algebra shuffle, look like that. Right? Is that all right? Right. One more detail. This is maybe a little bit unnecessary. I don't know. Right? Does anybody know what is 1 divided by cosine? Does anybody know? You guys ever heard of secant? Secant, right? So you know 5 newtons times secant of the angle. If you don't know that, but that's okay, right? I really want you to know divide by cosine. Okay, is it? Because hey, remember my calculator? Let me go back. Right, yeah. Hey, look at that. I've been doing 5 divided by cosine of something. I've just been popping in different angles. I said, I'll show you later in class where I can get it. That's it. That's what I've been putting in my calculator the whole time. You guys see that? That is this graph right here. It's the same thing. You see that is that graph? You see that? Okay. Let me show you guys this too, because I did graph this ahead of time. Do you guys know a program called Desmos, online Desmos graphing calculator, right? So I graphed secant of x. Oh, that's 1 over cosine, just multiplied by 5 newtons. That's this part of the graph right here. You guys see this part right here? You guys see it right here? Right. No, that is not a parabola. As somebody said, it's not a parabola. It's not a parabola. That's a secant curve, right? And it's going to run into this vertical asymptote. You guys see it's all the same thing? Right? All right. So we got that right there. Right there. All right. So are we good so far? All right. And then, yeah. So you can never make a perfect T from this point of view because there always has to be a vertical component holding up. Like if I go back to this poster, right? See, if you had a perfect T, then these components would go to 0, but that can never happen because they have to always be 5 and 5 to balance out with this 10 newtons. Okay? All right. All right. Oh, before I move on to the next one, let me show you guys a little bit more complicated version of this. Right? And you might have a textbook puzzle that's something like this too. Definitely my AP, I think my honors class will do something like this. My conceptual students might fall a little bit short of this, but how about this? What if you had an asymmetrical joint? So what if you're an engineer one day, you're designing a truss bridge. You got like a truss component this way and the component this way, and it has like some weight pulling down, right? And you got to figure out, oh, what's the force in each component? Because I have to know, let's say, what materials to make out of, what's the strength of these materials, how thick do I have to make this rod? Is it tension or compression? Right, that might help too, right? And then if I know how much material and how thick I have to make it, right, now I can say how much it's going to cost and come up with a contract bid or something. Okay, something like that, right? Okay, so it'd be a big old puzzle, but the guiding principle is all on this poster right here, where you can figure out, okay, so this guy's pulling up to the right, this guy's pulling up to the left, right? And then you got the weight pulling down. Now, if you introduce a Cartesian system, you can break these all into components. See, like, how much over, how much up? And you guys see the guiding principle is going to go, this guy pulls to the right as much as this guy pulls to the left. That's the blue ink right there. The sum of the forces in the x direction goes to 0. These two are the same magnitude, just opposite directions. Right? Here's a little bit more granular. So the right force times cosine of beta to the right minus the left force times cosine of alpha. That has to 0 out. You see that? Right? How about in the vertical direction? Let's go green ink. The sum of the forces in the y direction goes to 0. So this up plus this up minus this down also zeroes out. And that's exactly what this says right here. Here's left force sine alpha pulling up there. There's right force sine beta pulling up there. And there's the weight pulling down, so I'm subtracting it. Right, so up plus up minus down also zero that. Okay, right, you guys good? All right, so see something like that one day, so you're done. All right, next one. Oh, the chain gang. It's time for the chain gang. I'm gonna call this guy 1 kilogram, 1 kilogram, 1 kilogram. Of course, you could use different masses. That's okay too. Just doing example. Right. So we got these spring scales. Guys, the top spring scale holds up how much weight in newtons? 10, 20, 30 newtons? You guys see 30 newtons? Okay. What about the middle spring scale? How much weight does it have to hold up? How about just whatever's beneath it? Is that like 20 newtons of weight? Remember, 1 kilogram weighs 10 newtons on Earth. How about the bottom spring scale? How much weight does this guy hold up? Like 10 newtons? Something like that, right? You guys ever play a barrel of monkeys? Those little plastic monkeys with the hooks, right? What would it be easier to be? A monkey near the bottom where you just have to hold up your own weight? Or a monkey near the top where you have to hold up all your monkey friends? What's easier? It's probably easier being in the bottom, you guys think? Or how about this question? Got a heavy metal chain suspends a weight. Suppose it's metal chain's been hanging in a warehouse since like 1940. It's all rusted over. Right? Some of those links are about to go. Is which link is most likely to break first? One at the top. I think one at the top, right? You think? All right. Next scenario. Okay, this looks like the same thing except I just slipped in one more spring scale in the middle. Let's call this 1 kilogram, 1 kilogram, 1 kilogram. Okay. Is the top one still holding basically 30 newtons? You guys think? I'm throwing out the weight of the spring scale itself. 30 newtons. Okay. Do you think the bottom one's still holding up only 10 newtons? 10 newtons. Okay. What about the middle spring scales? Guys, does this go 20 and 20 or 10 and 10? 10 and 10. It splits. Right? Guys good? Right. Oh, I did miss one detail. Let me back up a little bit. Okay. Could you turn this sideways? Okay. Could this be a choo-choo train? Choo-choo. It's moving along. And say I got an engine in the front that's not only moving the boxcars behind it, but accelerating the boxcars behind it. So there's some kind of net force going on. Do you think it could be? And do you think the link, this link in the engine to all the cars behind it has to drag all the cars behind it? And that's a huge tension force. But as you go back towards the back, successively towards the back, do you think it's less and less tension force until the link that pulls the caboose at the back, that probably be the smallest tension force, do you guys think? Right? That's just a variation on the chain gang. Same thing. Okay. All right, so you guys good with that? Okay. All right. Have you guys noticed that all the ones on the front we've done so far are all static situations? Like they could all be at rest. So all the forces zero out. Okay. Now, when you get to the back, we're about to put some motion in this ocean. You guys see like accelerating up and down type? Okay. We're going back to some motion. Okay. So let me introduce some motion to you guys. So here, let's do some posters real fast. Let's do some posters. All right, so let's show you guys some laws of motion. Newton's laws of motion. There are these 3 laws of motion that you can tie all this back to. So first law of motion is also called the law of inertia. This is object at rest will remain at rest. An object in motion will maintain its velocity, speed, and direction of motion. That's what velocity is, right? And until then, I should say a net external force acts on that object, right? So for example, all the stuff in this room is just sitting at rest. It's not just going to spontaneously jump off, right? It's all either at rest or moving with the earth, however you think of it, right? And for anything to change its velocity, that can be speeding up or slowing down, or in a few weeks going around a curve, the only way for that ever to happen is there has to be a net external force. One of my classic examples is this Voyager spacecraft. It was launched back in the 1970s. It's been going for decades, right? And it's still going. It's still in motion. How much fuel does it need to keep going? Zero fuel. It's just going. It's just coasting from inertia. Okay. All right. So there's first law. Newton's second law of motion says, why does anything accelerate? Accelerate. Now you guys know what acceleration is. It's a rate change in velocity. Be speeding up or slowing down or going on a curve in the future. Right. Now we're saying how you get it. So why would anything accelerate? Well, because there's a force on it. And in fact, that acceleration is directly proportional to that net force and inversely proportional to the mass of the object. Okay, so more force, the more acceleration. Okay, so like a weight could cause a free fall acceleration, for example. Right? But more the mass, the less it will accelerate. Let me show that to you guys. So it's got little mass, big mass, and put the same force on both of them. Yes, they put the same force on both those objects. The little tiny guy, little tiny mass has a huge acceleration, and a large mass has a tiny acceleration. You guys saw it too? Okay. So there's Newton's second law of motion. Okay. So now you know where these accelerations are coming from. They're coming from a net force. A lot of times it's written this way, F equals ma, but I usually like the fraction form myself because it's like cause effect. Force on a mass causes an acceleration. Okay, that's good. Here, let's throw in here's third law real fast. this is the equal and opposite rule. So for every force, every active force by object A on object B, there's a reactive force equal to magnitude opposite direction by object B on object A. Right. So we get an explosion in a cannon on a cannonball and back on the cannon. It's equal and opposite forces. Or how about the Earth and the Moon pulling on each other? Equal and opposite forces. Okay. So this is all going to come up later on. Right. Right, let's look at acceleration as a bridge variable between everything we've been doing for the last 3 weeks and what we're headed into, well, starting about today. Right. So you guys remember those 3 kinematic formulas? Like x equals v naught t plus psi t squared, and you guys remember those 3? We've been using them over and over and over the last few weeks. Okay? All I did was I just rearranged them and to solve for a. So yeah, where's the a? Oh, here's the a. Each of those could be equal to a. Is that okay? You just rearrange it. Okay. That's what acceleration is. It's a rate change of velocity, and then in terms of, well, velocities or distances or times, it could be any of those things. Okay. And now here's Newton's second law of motion. Acceleration is caused by a net force acting on a mass. Right. Put it all together. So now you can bridge between what we've been doing the last few weeks and what we're going into. You guys get that? Okay. Okay. Good so far? So far? Okay. So one more thing, there's a bottom half of this poster, so don't worry about this so much for a while, but this is the rotational form. I have a turntable. Right? So what if things are like rotating, like spinning, right? So we're not ready for that yet, but when we get to it, there's a rotational analog for all this linear stuff, and it's just like that. All right, great. This is the future. All right, all right. Now we're finally getting to this one. All right, so this is going to relate to the this mini lab right here. So we'll look at this mini lab, and I'm going to bring that poster back up, and I'm going to make the connection. Okay, so here we go. So of course, it's good to start with labs because you guys get to explore stuff yourself and actually discover it yourself in the first place. Okay? So I had you guys take lab weight, scale, and I said accelerated upward. And what happens to the force reading on the scale? Now, if it's just hanging out at rest, there's some force reading, some number of newtons. Okay? And then now, I think the most obvious way to accelerate it upward is to pull it up faster and faster. Is that true? You guys, if you do that, if you pull up, if you like jerk it up really fast, does the force reading also go up? Yeah, it did. It did. So I'm going to say the force reading increase. Okay. Now, while I'm still on that one, there is a less obvious way to also accelerate upward. Guys, in this whole system right here, can you move it downwards, like a downward velocity, and it also accelerates upward? It'd be moving down doing what? How about slowing to a stop, right? And if you do that, it's kind of hard to capture on camera here, but you could say it in person. If I move this down at constant speed, which would be no acceleration, and then suddenly jerk it to a stop, do you see how the weight reading jumps up real fast, right? Of course, Earth's gravity pull doesn't actually change, but the spring scale force has to go up. That's also an example of this. Now, I'm calling this elevator weight. So if you stood on a bathroom scale in an elevator, it'd be the same effect. If you started at, say, the ground floor and then start moving upward, that's a brief upward acceleration, you're going to feel heavy just for one instant. Now, when the elevator is going up at constant speed, is that acceleration? No. Actually, can you even tell the elevator is moving at all if it's moving at constant speed? Not at constant speed. Now you can feel it when it gets to start moving when it comes to a stop, but not constant speed. You have no idea how fast it's going or if it's moving at all. So it's just like sitting in this room. Okay. So it's all that. So for completion, if you're in an elevator that's coming down and it comes to a stop, say you're on the top floor and come down to the base floor and comes to a stop, you also feel really heavy just for a moment. That's fine. Right. Now let's move on to the other one. What if you accelerate down? Now, I think the most obvious way to accelerate down is to move it down faster, faster, faster. In fact, an extreme example of that, sometimes if you take things to extremes, it really eliminates the situation. What if you just let it go? It just go to the edge of a cliff and just free fall off a cliff. Guys, if this is free falling off the edge of a cliff, how many newtons is this reading? 0. It's like floating around like an astronaut. Is that true? If you go in an elevator and you cut the cable, you'd be floating around like an astronaut. Is that true? Right? So that's an extreme case, but in general, accelerating down, it's going to be a decrease in that force reading. Okay. Right. Is that okay? Right. And for completion here is what's the less obvious way to also accelerate down? Can you move this whole thing upwards while it's accelerating down? It's moving upwards doing what? bring it to a stop, right? You can kind of see that here, right? Kind of hard to capture on camera. But if I lift this at constant speed and then I suddenly bring it to a stop, you see the force reading like jumps to 0 briefly. Right now, it's just real brief, but that's also true. Okay, you guys get that? Right. Okay, let's come up with some math for this. Right, and that's what this poster is all about. Right, so let's bring this poster. Right, so zoom out. You guys can see this. There you go. Right. No, this whole poster is only for an upward accelerating elevator, which again might be zooming up faster, faster, faster. Oh, here it is, moving upward and speeding up. Or don't forget this one. You could be moving down but slowing to a stop. So it's downward velocity, but still upward acceleration. So this is upward accelerating. And those two situations are physically identical. Like if you're inside and you're standing on this bathroom scale, you don't know which one you're doing. Okay, let's go up. Okay. Notice I have a free body diagram. Let's look at this free body diagram. Here's an object standing on a bathroom scale. I have two forces. Here's the weight, Earth's gravity field pulling up, mass times gravity field. Is that okay? The weight, right? And here's, I'm going to call this the normal force. Normal just means perpendicular. Guys, if you stand on a flat floor, is that floor pushing straight up on you? It is, right? And that's a perpendicular. That's what N for normal means. Okay. Okay. And if you're accelerating upward, do you think the overall upward force has to be more than the downward force? Okay. And so if you normally weighed like 100 pounds, then on this scale, maybe you read like 120 pounds. Okay. You read more than your usual weight. Okay. Let's look at the math. So here's Newton's second law of motion. Net force equals mass times acceleration. Well, the net force is just, in this case, the difference between this up and this down. Is that okay too? Right. Now let's put it all together. We're going to put these two guys together. So here's the net force, which is the normal force minus the weight. And that's, here's Newton's second law of motion equals an A. Right, is that okay so far? Right? Okay. Now let's solve for the normal force. Can I just take this mg and slide it over? It'll look like that, right? A little algebra. Okay. Then if you want to, you could also factor out the m, and it could look like that. Okay. So here's the scale rating as a function of the motion of the elevator, right? And your mass, and hold it up, right? Okay. And the gravity field of the Earth. So the more you're accelerating up, the more the force rating is going to be. Right? Now, what if you were accelerating down? Do you think the scale rating would be really tiny? Do you think? Right? And how would this math change? Instead of being a plus here, what do you think that would be? Probably a minus. Right? We'll show you guys that one. I didn't quite try that, but you could probably figure out that it would work out that way. Here's the three scenarios: accelerating down, accelerating up, and equilibrium is not accelerating at all, which might be at rest, or constant velocity, which might be moving up or moving down. But if you're standing outside of the elevator, you can't distinguish the difference. Right? Remember, guys, there's a bunch of scenarios here. Accelerating down might be, accelerating down might be moving up, slowing to a stop, or moving down faster, faster. Accelerating up might be moving up faster, faster, or moving down, slowing to a stop. And equilibrium might be at rest, or moving up constant velocity, or moving down constant velocity. And if you're inside an elevator, if you're inside, it's kind of hard to distinguish between which scenario exactly. Right? All you know is you're in either this, or this category. Okay. Right. And here's the equations. Right. So here, just to run one of these, let's do accelerating downward. Right. The extreme situation is you could cut that cable. Guys, if you cut that cable, how much are you accelerating down? Would that be the full free fall rate of gravity? What is G minus G? Is that 0? 0? Okay. And if you cut the cable, is the tension in the cable also 0? I just swapped that out to cable tension. So just to be familiar with that. Could be normal force, could be cable tension. It's the same math, right? So if that's 0, that's 0. Yeah, that's 0, that's 0. That's true. All right. All right. All right. Oh, you know what? Here, real fast. You guys did have pulleys back there. I saw a few students setting up some of these Atwoods. So this is going to be a lab one day. We're not quite ready for this, but we're getting closer. All right. Moving on. This one was really similar. What if you throw a string over and you do, we got 4 different categories, 4 different scenarios. What if you take the top spring and move it to the left, speeding up? What happens to, well, either the tension in the string or the spring scale reading? Do you think it would also go up? You jerk that to the left? I think that would increase. What if you take the top spring scale and move it to the left, but slow it to a stop? Do you think it puts a little bit of slack in the string and the spring scale readings go down? Or you think about it in terms of the vertical one, right? If it's moving up and slowing to a stop, right? So that'd be like less tension in the string. So that'd be like decrease right there. Right? Or if the top spring's moving to the right and speeding up, back in extreme case, you could just let it go. And this one could be accelerating down, close to free fall. Right? That would also be less tension in the string and also the spring scale readings. And finally, for completion, is the top spring scale is moving to the right but slowing down. So moving to the right, but bring it to a stop. Do you think that the string tension has to increase massively to also maybe slow this one down to a stop? Right, so that'd be an increase in tension there. Okay, something like that. Friction. So say lifting force, I'm going to make up some numbers. So let's say 10 newtons, 5 newtons, and then to drag it across the table. Suppose it was like 2 newtons and then like 1 newton. Right? You guys see like the ratio would be pretty well constant, right? That force compared to that force. That's called coefficient of friction. So Greek letter mu. 2 over 10, 1 over 5. That's like 0.2. You guys see that? Like 0.2? Right, so ratio. Usually that number is less than 1, which means it's easier to lift the object than to drag it. Right? And most guys get this pretty good. Right? That's not necessarily universally true. Guys, what if you drag this across wax paper or sandpaper, right? Different types of surfaces? I bet that these dragging forces could change because this coefficient is changing. Right? 2 over 10, 1 over 5. That's pretty much that. Right? Do you think, what if you have brand new tires on a car and you have a well-paved road and you try to lift the car and it's really hard to lift the car, that takes some force. And you try to push the car across the pavement. Let's say the wheels are locked. So it's like sliding across the pavement, right? If this number is over 1, which it might be like 1.1 for tires on a road, it would actually be easier to drag, so easier to lift the car than to drag it, right? Although that's really rare, right? But it could happen, right? If you have some circular motion, right? Now this one I left purposefully kind of ambiguous because it depends what type of circular motion. So do a couple scenarios real fast. If you do a conical pendulum, then the answer is always the spring scale force is going to be more than the weight of the object. Right? Here's why. That spring scale force has to both hold the object up and also pull the object in. It's called centripetal force. We'll talk about in a few weeks. Right? So the hypotenuse of this triangle is always more than the weight of the object itself. Right? But what if you had a different interpretation? What if you do like a vertical loop? And what if you do loop it around really slow? So it's like, just barely gets around the top. In that case, the answer might change from like that answer to that answer. And so which force is the greatest force? The weight or the spring scale force? It depends how you interpret that. All right, and last one. If you guys got time to get to this one, if you dunk it in water, guys, if you dunk it in water, do you think the scale rating goes down a little bit? Goes down a little bit, right? In fact, it would decrease more for less dense objects is how it works out. That's called Archimedes' principle. We're going to get to this one next semester, but throw this up here. Suppose you have the weighs 10 newtons. You guys see 10 newtons? There's your biggest lab weight, right? And then you dunk it in water. Suppose the reading goes down to like 7 newtons. Okay? Turns out that support force from the water, which is called the buoyant force, it's also holding it up a little bit, is exactly equivalent to the weight of the water displaced. So if you have do you guys see this little overflow tube? Right, and it catches in this bucket over here, right? So if the water flows out because this object is displacing some water, and you catch all that water and you weigh the water, it exactly represents the difference. So if you go from 10 newtons down to 7 newtons, got a difference of 3 newtons. That's the weight of the water displaced. Right? And then here's another form. This is called Archimedes' principle. All right, so you guys good there? All right, so that is our wrap on today. You guys have a good afternoon. See you tomorrow.